Great. Hello, everyone, and welcome to phyloseminar.org. It's been known for decades that certain polynomial relationships hold for data generated from a tree. These were first discovered in a pair of 1987 papers, one by Lake and one by Cavender and Felsenstein, and have obtained the name phylogenetic invariants. Mathematically speaking, invariants belong as a subject in algebraic geometry and thus have been extensively studied by mathematicians. Practically speaking, invariant methods have thus far had limited impact on inference, although it appears that this may be starting to change. In this series of 3 talks, we're going to hear 3 perspectives on invariants and how they may be used to make inferences. We will start with Marta Casanellas Rius, who will give background and bring us up to date with research on invariants. Then we'll have Laura Kubatko describe coalescent-based inference using invariants. And third, Barbara Holland will describe Markov invariants and how they differ from classical phylogenetic invariants. I want to remind people that the Q&A app is gone now, so you can ask questions through Twitter or IRC, as described in the attending section of the Phyloseminar website. As I mentioned, today's speaker is Marta Casanellas Rius. Marta has spent most of her career in Barcelona, starting with her undergraduate and graduate work in theoretical algebraic geometry. She had a Fulbright fellowship to do a postdoc with Robin Hartshorn, who is a leading algebraic geometer at UC Berkeley. In 2004, she turned her interest towards applications of algebraic geometry to phylogeny and then has been a leading researcher in the field. She is now an associate professor in the Department of Mathematics at the Universitat Politècnica de Catalunya. Welcome, Marta, and thanks for participating.
Thank you, Eric, and thank you for organizing this nice seminar that I don't follow online usually because of matters of time, but I usually follow afterwards in YouTube. So should I start?
Yes, please.
Okay. So I'm going to try to present some work on phylogenetic invariants. I'm going to do an introductory talk, and part of the second part of the talk, maybe I will explain a little bit of nowadays research on this topic and joint work with Jesus Fernandez Sanchez. So let me first roughly explain the story of phylogenetic invariants. They were introduced by biologists in the 80s by Lake and independently by Cavender and Felsenstein. And afterwards, there were some attempts to use invariants and some developments on phylogenetic invariants in the 90s, but some simulations, some results on simulated data conclude that they were not very useful to obtain the tree topology. The problem is that not all invariants were known at that time. It was also not clear how to use them, and sometimes they were evaluating at the same time the tree topology and the fitness of the model to that data. But in 2004, in Felsenstein's book, it's written, invariants are worth attention, not for what they are, for what they do for us now, but what they might lead to in the future. So I'm going to try to explain what this is. This is the future now. So I'm going to try to explain what can do invariants. Invariants can deal with very general models. That's the most important point. Like general Markov model, which does not assume stationary distribution, nor time reversibility, nor global homogeneity, nor even local homogeneity along edges, can deal with mixtures, or the fully partitioned model, as it might be also known, or even with a coalescent model. Okay, I'm going to try to explain a little bit what this is. Nowadays, I would say that the theoretical issues are solved for the basic models, including the general Markov model. They have widely been used in identifiability problems, explaining whether a model is actually identifiable or not by work of Allman and Rhodes. And there are nowadays successful reconstruction methods for quartet trees based on invariants, mainly Eric +2, which is one of the methods I will explain, and also other methods by other people like SVD quartets or using the squangles. Okay. So here's the outline of the talk. First, I'm going to try to explain which type of evolutionary models we deal with. Then I would turn my attention to phylogenetic invariants and explain what they are. And at the end, I'm going to talk about these new methods to use phylogenetic invariants for quartet reconstruction. Okay. So the main goal for us is going to be to reconstruct the tree topology and not the branch length. Okay, so the tree topology, for example, for quartet trees, and we have these 3 trees, and we will use this notation: 1, 2 against 3, 4 for this tree, 1, 3 against 2, 4 for this other tree, and 1, 4 against 2, 3 for this tree. And our input in order to obtain the tree topology would be an alignment of DNA sequences. I'm going to stick to DNA, but we could also use protein sequences. Okay. So what type of evolutionary models we consider? In order to model the evolution, for the moment, let's assume that sites in the alignment are independent and evolve according to the same process, are identically distributed, so that we can model the evolution of a single site on a tree. We put at each node of the tree a random variable taking values in the set of 4 nucleotides or in the set of amino acids if we were dealing with protein data. And the nodes at the leaves are observed nodes because the alignments, the columns of the alignment give us observations of these random variables, whereas the nodes at the interior nodes are hidden. We don't have observations of them. We assign a distribution, I'm going to call it P, at the root of the tree. We are writing here a rooted tree, but usually we consider trees unrooted trees without root. Okay. But in order to explain the models, it's much better to use a rooted tree. And at each branch of the tree, we write a transition matrix that collects the conditional probabilities of a nucleotide at the parent node. I label the rows by the parent node, and I label the columns by the child node. And the answers of the substitution matrices are the conditional probabilities that a nucleotide mutates to another nucleotide at the child node. This transition matrix is different for every edge of the tree. That's why I call them S sub I. As they are conditional probabilities, the rows sum to 1. Okay. As I said, we could also consider amino acids or any other finite set of states and model evolution in the same way. The entries of the transition matrices and the root distribution are going to be the parameters of our models. We don't know them, but we don't want to infer them either. According to the shape of these substitution matrices, we can deal with different evolutionary models. We can put restrictions on this type of matrices, and we can get very restrictive models like Jukes-Cantor or the most general Markov model. Okay, so Jukes-Cantor would be like put the uniform distribution at the root of the tree, which coincides with the stationary distribution in this case, because the matrices, the substitution matrices in this case, have only 1 parameter per no mutation, the B here, and 1 parameter for mutation, for non-mutation. So this is the parameter for the substitution, the probability of substitution and probability of no substitution. As I said that the rows sum to 1, we have this condition here, and actually there is only a single parameter per edge. Okay, this is the most restrictive model. And on the other side, we have the general Markov model, which means we don't impose any symmetry or any condition on the transition matrices. And at the root, we can put any distribution. Put an arbitrary distribution at the root and let the substitution matrices be whatever. As rows sum to 1, we have 12 free parameters for each transition matrix. And there are many models in between. There are the Kimura 2 parameters, Kimura 3 parameters, something that is called the stand-symmetric model. But I add the word general here because Kimura 2 parameters and Kimura 3 parameters in this setting are not the same as the ones biologists mostly used. And I'm going to explain why I use here general. So what is common in biology is to model the evolution by a continuous time process. So one assumes that there is an instantaneous mutation rate, and this rate is the same throughout a branch on the tree, and these rates are collected in a matrix that is called the rate matrix Q. so that the substitution matrix is actually the exponential of this rate matrix times the elapsed time along that branch. Okay. What does this imply? This implies that as we have a constant rate along the branch, this implies what can be called local homogeneity. Okay, same rates along the branches. These type of models have one problem, that if you want to use different rate matrices on different branches, and you want to concatenate two of these processes, so I have one process and then it's followed by another process, then the product of these two matrices is not of this type in general. So the concatenation of two processes of this type doesn't have to be a continuous time Markov process. Okay, so that's why often global homogeneity is assumed, that the rate matrix is the same throughout the tree, and it's called the rate matrix Q. Okay, this is called global homogeneity because we assume that along the whole tree, the instantaneous mutation rates are the same. This in particular implies that the process is stationary, because there is a stationary distribution, it satisfies this condition. And usually also time reversibility is assumed, that this matrix is symmetric so that the process can be reversed. Okay. On the other hand, the general Markov model I was presenting, the parameters are the entities of the transition matrices and the distribution at the root, not the rate matrices. Okay, and in general, not all substitution matrices are of this type. For example, there is a new paper in Archive where Fernando Sanchez and Roca, they prove that for the general Kimura 3-parameter model, only 1/4 of the matrices are of exponential type. So considering the transition matrices directly and not the rate matrices and the as parameters and the time, gives too many more matrices than this type of matrices. Okay. And as a summary, general Markov model does not assume a stationary distribution along the tree, does not assume time reversibility, nor even global homogeneity, and even not local homogeneity along branches. So along a branch, it could have happened that there was a mutation rate for a while, and then another mutation rate for afterwards, or even another one. Okay. Different mutation rates along a branch. So for example, what's the difference between general Markov model and GTR? If we consider this tree, we place the root here, then the number of parameters for general Markov model will be 3 parameters for the root distribution. For each transition matrix, we have 12 parameters. So as we have 5 transition matrices here, we have a total of 63 parameters. Whereas for the GTR, we have 3 for the stationary distribution. For the rate matrix, as it has to satisfy the time reversibility, and they are usually normalized, so the branch lengths correspond to the expected number of mutations per site. We have 5 parameters actually. We have 5 branches, and therefore we have 5 branch lengths. So in total, it makes 13 free parameters for the GTR. Okay, that's here another way to see that general Markov model is much more general. The problem is, how can we deal with such a big number of parameters? We really don't want to estimate them. It's going to be it's going to lead to bad estimates of the parameters. Okay, and here is where phylogenetic invariants come in. So, I'm sorry, I was drinking water. So, once we have fixed a model on a phylogenetic tree, we can write the Jones distribution at the leaves of the tree. If I let this leaf be in a state x1, in nucleotide x1, and this leaf in x2, and this leaf in x3, I can write the probability of observing these 3 nucleotides at the leaves as the sum over all interior nodes, the probability corresponding to the root, to the state at the root. I'm going to call YR the state at the root, Y4 the state at this interior node, and then multiplying by the transition matrices, the corresponding entry of the transition matrices. So if I had these nodes observed, then the expression would be only this, but as I don't have them observed, I have to marginalize over them, and I have this expression here. The good thing for people who used to work in algebraic geometry as me is that this is a polynomial in terms of the parameter of the model. We have estimates of these probabilities here because the columns, the relative frequencies of the columns of the alignment provide me estimates for this joint distribution. What I don't have is the entries of this expression here, the entries of the substitution matrices nor the root distribution. So are there some constraints among these probabilities, which are the one I know, that are satisfied no matter what the parameters are? So are there constraints that can be used to reconstruct the tree topology without having to estimate the parameters? That's the main goal, the main idea behind phylogenetic invariants. Let me put an example. Let's consider the Jukes-Cantor model. There are some constraints, like the trivial constraint that sum of all probabilities must be equal to 1, that's for sure. And there are some other constraints like this one. If I have the Jukes-Cantor model on any tree, then the probability of observing nucleotide A at all leaves is the same as observing nucleotide C or G or T. So I have this equality, no matter what the parameters of the substitution matrices are, that these equalities hold. And no matter the topology of the tree actually doesn't matter either. The same here. The probability of observing A's at all leaf except 1 is the same whether I observe instead of A, I observe T, because the root distribution was uniform and the substitution matrices just had one parameter per no mutation and one parameter per mutation. So it's actually, these equalities hold wherever the parameters of the substitution matrices are. And as these equalities do not depend on the tree topology, these are called model invariants. They are relations satisfied by this model on all the tree topologies. But there are some relations that could aware more interest because they depend on the tree topology. So phylogenetic invariants of a tree were defined as those polynomial relations, those constraints that are satisfied by any joint distribution that has evolved under a fixed evolutionary model on the tree. And we call topology invariants. This is a new notation because sometimes these were called phylogenetically informative. There has been different names given in the literature, but in the new book of Mike Steele, it's called like this, topology invariants. These are phylogenetic invariants, so constraints of this type that are satisfied by any distribution on the tree, but are not satisfied on some distribution on another tree topology. So they tell us something about the topology. They hold for a particular topology, but not for all other topologies. So they could, in theory, be used to distinguish between different topologies. For example, let's put an example of a topology invariant. These were the first invariants that were known by Lake. Let's consider this quartet tree. Let's consider the Jukes-Cantor model and consider the following equation. The probability of observing 4 nucleotides, X, Y, Z, W are nucleotides, any different nucleotides. So let's fix X, Y at the leaves 1 and 2. And at the leaves 3 and 4, we can either consider XY here or ZW, ZY, XW. It's not difficult to see that this probability, the sum of 2 probabilities here, is equal to this other sum of 2 probabilities for this tree topology, for this quartet tree. Okay, because here we have leaves 1 and 2, they always have XY here. Okay. In the same way, this other equation is the same as the one above, but just exchanging the roles of leaves 3 and 4. H1, this equation here, does not hold for this tree topology. So if instead of this quartet tree, I had 1 and 3 here, and I write this equation this does not hold for all distributions on this other tree. So therefore, this is a topology invariant. And the same for H2. H2 is not a phylogenetic invariant for this other quartet tree, so it is also a topology invariant for this tree. Okay, these are very simple equations. They have degree 1, so they are polynomials, but of degree 1. They are interesting for some things, but are not very interesting for topology reconstruction, as Hulsenbeck proved in some simulations. So for mathematicians, the set of distributions under a particular model on a tree topology is a subset of the space, like could have, for example, this shape of this surface. And just considering linear invariants of degree 1 is like looking at the smallest box that contains it, but not looking actually at the shape of the surface. So we would like to consider more accurate thing, something that approximates better the surface and not just a single box. Okay, so then we would have to deal with higher degree polynomials. And then we have a problem. How do we compute higher degree invariants? We can write the joint distribution in terms of the parameters, the substitution matrices, and the root distribution, and put this in a computer and try to get the invariance from that. The problem is that the computer, the RAM memory is limited, and we cannot get invariants for trees larger than 5 leaves. Okay, and even if we manage to get them, for example, for the Kimura 3-parameter model, for a quartet tree, we managed to get 8,002 phylogenetic invariants, like this one. So this is a very ugly polynomial, and as you see, it doesn't stop here, it keeps going. We got this using a trick, converting the parametrization to some monomials. But the thing is that we cannot give this to biologists because they are not going to use it. It's impossible to use. How can you use such an ugly polynomial? So let me tell you some good news. There are some invariants of high degree that are very easy to obtain. For example, let's consider the general Markov model on this quartet tree and consider the vector of joint distribution, this vector here, and rearrange it in a matrix in the following way. We call the flattening matrix according to the bipartition 1, 2, 3, 4. The rearrangement of this vector into this matrix where the rows are labeled by the states at the leaves 1, 2, so that we fix state AA throughout the row, HC throughout the row, and TT at the end. And the columns are labeled by the states at the leaves 3, 4. So 3, 4 have states AA here, AC here, and so on. So this 215 components vector is rearranged into this 16 times 16 matrix. And the result is, if P is a distribution coming from this tree topology, this tree that splits 1, 2 against 3, 4, then the flattening, putting here leaves 1, 2, and here leaves 3, 4, is a matrix of rank lower than or equal to K. And if not, if this P, this vector distribution, this distribution doesn't come from this tree topology, it comes from another topology, another quartet tree, or comes from wherever, then this matrix would have rank 16. So this result, as was independently discovered by Amon Rhodes and Erickson, says that there are some polynomials which are actually the 5 by 5 minors of this matrix that are topology invariants for this tree, and similarly we can get topology invariants for the other quartet trees under the most general model, the general Markov model. Okay, so there are even better news, because we can relax the assumption that positions evolve in the same way, exactly with the same process. We keep the assumption that positions are independent, but we assume that they just evolve under the same model, the same evolutionary model. For example, the general Markov model, but we let some parts of the alignment evolve on the tree topology T with certain substitution matrices. Some other part of the alignment evolve on the same tree topology, but with some other substitution matrices, and we could consider even more partitions of the alignment. So this we would say that P is a mixture distribution of M partitions. We partition the alignment into M sets, okay? And the nice result is that if we have a bipartition of the set of leaves that comes from removing a split, an edge of the tree, then, as before, the rank of the corresponding flattening of the distribution, so rearranging the distribution according to the leaves where they are split into this bipartition, would have rank 4 times M, where M is the number of partitions I'm considering, okay? Or in terms of polynomials, this says that the 4M plus 1 times 4M minus of this matrix would be polynomials that vanish on the distributions arising from a tree that has this internal edge. This that has an edge that when we remove it, the set of leaves is split according to this bipartition. Okay, I'm going to come back to mixtures later. So we have seen that it's difficult to obtain invariants. Computers cannot do it, and they can't do it for n leaves, where n is any number. Some of them can look pretty bad. The main thing would be considering that we are only interested in topology invariants, because, as I said, our goal would be reconstructing the tree topology and not the branch length, nor evaluating the model, nor anything. Okay, so it's hard to decide which invariants are phylogenetic invariants. I meant here which invariants are topology invariants. I meant. We already saw that there are some nice invariants known for any number of leaves, the edge invariants. I presented them for quartet trees, but we can extend them for any number of leaves. And the nice result is that for any tree on any number of leaves, any tree evolving under the the general Markov model or one of these general submodels, then if you only want to reconstruct the tree topology, it is enough to consider this type of edge invariance, these conditions on the rank of certain matrices that we call the flattening matrices. So these are these conditions are easy to evaluate. Okay, actually, this result is not so surprising because we already knew it in combinatorics. In combinatorics, there is this result of Buneman that says that a tree can be recovered by knowing all the splits, all the bipartitions that it induces on the set of leaves when you remove the edges.
So Marta?
Yeah.
So if I understand correctly, you're not saying that every topology invariant is an edge invariant. You're just saying that there's enough edge invariants to give you the correct topology.
Exactly. I'm not saying that every topology invariant is an edge invariant. I'm just saying that it is enough to consider edge invariants in order to recover the tree topology.
Great, thanks.
Okay, and this is analogous in algebraic geometry. This is the analogous of the combinatorial result of Bunemann's. Okay. So I was talking here about minors of matrices, but actually this is not the best way to use this condition on the rank of the flattening matrices. There is a new approach introduced by Erickson, which is using the singular value decomposition. What is this? If you are given a matrix like that flattening matrix, and you want to evaluate the distance of a matrix to the set of matrices of rank less than or equal to 4, let's say, you can do the following. You can compute the singular value decomposition of the matrix, which for non-mathematicians, you do not need to know what it is, but it's writing the matrix as a product of 3 matrices. These 2 U and V are orthogonal matrices, whatever that means. And the matrix in the middle is a diagonal matrix. In the case when we have, if we have square matrices here, then this is diagonal matrices, and its entries are ordered and are positive. And then there is this Eckhart-Young theorem, or also a Smith theorem, that says that the distance from your matrix to the set of rank 4 matrices is given by the square root of the squares, the sum of the squares of the last singular values. These are called the singular values. If you take sigma 5 up to sigma m, and you compare the square root of the sum of the squares of this gives you the distance. So how far is your matrix from being a rank 4 matrix? This is in the Frobenius norm, which is also not relevant here. So what's the idea of Erikson's SVD method? In order to evaluate whether this bipartition or this split of the set of leaves actually comes from removing an edge of the tree, you compute this distance. If this distance from the flattening matrix to the set of matrices of rank lower than or equal to 4 is small, it means that this is probably a bipartition that arises from an edge of the tree. Okay? And then he tried to use this score in order to find first the best chair in the tree, so looking at bipartitions of 2 leaves against the others, and then proceeding in a recursive algorithm. Then once you have the first cherry, you join these 2 sequences, and you always treat them together, and then you add more sequences, and well, like a gridding algorithm, you obtain a tree. Okay. The problem with this method that was published in the algebraic statistics for computational algebra book, for computational biology book, I mean, the problem is that it's not fair to compare splits, to compare these scores for splits of different size. So this method actually, it might not be statistically consistent. And in simulated data, it was proved that it doesn't perform well when there is the presence of long branch attraction. Okay, so what's the problem with this method for this second issue? Let's consider this tree in the Felsenstein zone, where species 2 and 4 are close together, but the true tree topology is this one that splits leaves 1 and 2 against 3 and 4. And let's consider the wrong flattening, the flattening where I consider the bipartition 1, 3 against 2, 4. I simulated data on this tree, and I did the flattening matrix, and I observed that these columns, AA, CC, GG, and TT, if I sum them, they have most of the weight of the whole matrix. So the matrix is mostly concentrated on these 4 columns, and this makes this matrix have almost rank 4, while this shouldn't have rank 4 because this bipartition doesn't come from this tree. Okay, so that's one of the problems that the original Eric SVD method had. You cannot evaluate the rank of a matrix. You cannot put a score on the rank of the matrix if you don't scale the columns or the rows of the matrix to the same amount. Okay, so we modified this method just by considering dividing by the sum of the rows here, and so we consider the flattening matrix. Instead of directly considering the flattening, we divide by the sum of the rows, so that in this matrix all rows sum to 1. I'm saying sum of rows, and so these rows sum to 1. And I do the same with the sum of columns. So I normalize by the sum of columns, and so that in this matrix all columns sum to 1. So now I have, instead of 1 single matrix, I have 2 matrices, and we do the average score of these 2 matrices. So this is going to be the Eric plus 2 score. So the lower this score is, the most likely that this split A from B comes from an edge of the tree. Okay. We can do this not only for rank 4 matrices, but for rank 4 times m matrices in order to use this method for mixtures. Okay, so I would do the same, but instead of putting a distance to rank 4 matrices, rank 4 m. Okay, sorry. And the problem is that we don't infer this number of partitions, m. It is something that you have to input to the software. Okay, you can download this ERIC+2 method, this web page, or you can look at GitHub also, I think, and it's implemented in Pound. Has been implemented recently in Pope, so you can use it even for mixture, but input the number of partitions, please. So how does it perform this method? In order to assess the performance, we used an approach of Hulsenbeck. We consider this tree space. We consider trees with a parameter A for this branch length, a parameter B for this outer branch length, and we let A run here, B run here, so that the trees that we got on this corner are of this type in the Felsenstein zone, and we get all this range of trees. Okay, we simulate data on this quartet tree. For each pair of branches, so for each square here, we simulate 100 alignments on under this tree topology, and we try to reconstruct the topology using our method or comparing with other methods. If a method has 100% success, we put a black dot, and if 0%, we put a white dot and the grayscale in between. Okay, so for example, when we compare our method against the original ERIC SVD method, we realize that our method performs better on the Felsenstein zone. So ERIC+2 was inconsistent mainly in the Felsenstein zone, or at least you needed many more data to make it work on the Felsenstein zone. This is for 10,000 base pairs, okay, and data simulated under the GTR for a fixed rate matrix. How about other methods? How does the comparison with other methods? Here is method ERIC+2, neighbor joining. We simulated data under GTR. So neighbor joining here uses paralinear distance, and maximum likelihood is here, is estimating GTR. Left column is 1,000 sites, and the other column 10,000 sites. Okay, so we see that for 1,000 sites, our method performs more or less equal to the other to neighbor joining, and a little bit worse than maximum likelihood. But for 10,000 sites, it performs slightly better. These numbers here are 99% here of successful reconstruction and 98% here against neighbor joining, which is a bit worse. But if there is not so much difference, why should we use this method, ERIC+2, instead of maximum likelihood, for example? The thing is that you can use data generated under this much more general model, the general Markov model. So here we simulate data under the general Markov model. Will a maximum likelihood estimate a continuous time model, not time reversible though. And we let NJ be with a paralinear distance. In this case, maximum likelihood, of course, it performs worse because the model doesn't fit, the model it estimates doesn't fit the model that simulated the data. And our method keeps working well for a big number of sites, 10,000 sites, okay? What is this method robust enough? We try to violate its assumptions. Instead of generating data under the general Markov model, we generate on a continuous time model with gamma rates across sites. Here we let the parameter alpha on the gamma distribution vary a little bit. And here we plot the percentage of correct trees. This is ERIC+2, and this is maximum likelihood. And this is the original method of Ericsson. So compared to the original method of Ericsson, is quite robust. This is for 1,000 sites, and when we get to 10,000 sites, it performs as well as maximum likelihood, even if this simulated data does not fit the general Markov model we were considering. Okay. What is also good about these methods, that they can deal with mixtures. So let's consider this data of this paper, where you consider this tree topology, AB separated from CD, and this branch length in half of the alignment, and this other branch length in the other half of the alignment. Then we can use our method with a single partition, this is the number 1 here, or our method with 2 partitions. With a single partition is this thin line here, it doesn't perform that well. Maximum likelihood, maximum parsimony, maximum likelihood even with 2 categories are more or less doing the same things, okay, except maximum ERIC plus 2 with 2 partitions that performs a bit better. And when we go to 10,000 sites, ERIC plus 2 is the only one that performs actually good. Okay, maximum likelihood is not performing good because this data doesn't fit the model it uses. Okay. So what about larger trees? These were studies for quartet trees. This is something that still has to be solved, how to deal with partitions, with larger partitions, and compare different splits of different sizes. But in the meanwhile, we have used ERIC plus 2 to evaluate as the input of quartet-based methods. In order to do that, we convert the scores to weights for each tree. So we reverse the score, we invert the score, and normalize by the sum of scores, so that we have weights. If the weights were 1, 0, 0, this would mean that our tree topology is T1, and so on. If we have weights closer to 1/3, 1/3, 1/3, it means that the tree topologies are almost undistinguishable. Okay, and the idea was to use this is unpublished work, is to use this in quartet puzzling, in the Wilson method, and in weight optimization. We use this also in real data before using it as input of quartet-based method. We use the real data of Rokas and others for yeast, 8 species of yeast. This is supposed to be the correct topology. This is what some methods get. It's known that in order to get the correct topology, you should use 2 discrete gamma categories plus invariant sites. The problem with this method, ERIC plus 2, and all the other methods based on these flattenings, is that we cannot put directly gamma rates or invariant sites. We just have to consider 1, 2, plus 1, 3 mixtures in our case. Okay, so let's compute how many quartets for this data we got compatible with T or compatible with T prime. For the original method of Ericsson, there were more quartets compatible with T prime than with T. But for ERIC plus 2, even if we consider a single mixture, we get more quartets compatible with T than with T prime. And we get best results when we consider 3 mixtures here. And here for comparison, maximum likelihood with 2 gamma rates plus invariable sites, or 3 gamma rates. Okay, that would be the best, the model that fits better this data. And it's nice to observe that for the quartet that we didn't get correctly, the scores, the weights of these quartets are about 1/3, 1/3, 1/3. So that the 3 topologies, the quartets, are not highly distinguishable. Okay, if we remove this type of trees that are this type of quartets that are not highly distinguishable, then we get 100% of quartets compatible with the correct topology. And in order to evaluate ERIC plus 2 as the input of quartet-based methods, we use the approach of Rangwell and Gaskell. They generated data on these 3 different topologies. This is the worst case because we have many long branch attraction here and here. This is long branch attraction here, and this doesn't almost have long branch attraction. And there is this V parameter for the internal ledge, and the long branches have either 9V or 8V. So for the first topology, the easy one, when we use ERIC plus 2 with quartet puzzling or with Wilson or with weight optimization, what does it happen against the other method? Here we are computing the Robinson force distance to the correct tree, and we get much better results with ERIC +2 than with the other methods that get bad results because we are generating data under the general Markov model. For the CD topology, which was a bit more difficult, we still have better results for the ERIC +2 method, although it's getting a bit worse. And for the DD topology, which is much worse, we have also better results for the ERIC +2 method. And these results are comparable to a global neighbor joining tree. What if we simulate this was with data simulated under general Markov, but if we simulate under GTR data, for this very bad topology, the results are much better and also comparable to a global neighbor joining on these sequences. Okay, because the data doesn't have that much variability when we use GTR method to simulate than general Markov model. So just to finish, other uses of invariants, a paper that I like a lot by Allman, Kubatko, and Rhodes. They use these scores to evaluate the distance of a flattening to rank for things in order, for example, to assess how do the branch length change along a whole genome. This would be this would represent the line of the whole genome, and they are using a sliding window and plotting these scores for one bipartition and another bipartition. The red is one bipartition, the black is another bipartition. These are the scores, like the SVD scores, and you see there is a jump when the branch length change because they simulated this data. They know that the branch length change, and the scores are inverted when the split is not, the split 7-9 is not correct. Not correct. The correct split is 8-10, for example. So these scores detect the change of branches and the change of tree topologies. I must say that there has been that the invariants now have been used for more than 10 years, and there are different approaches, and they have different used in different settings. There is some nice work recently by Schiffman and Kubatko on trying to obtain the species tree under the coalescent model. There have been other approaches directly using the invariants and not the SVD method by Rusinko and Heap. Invariants have been used in many studies of model identifiability. When a new model is introduced, whether it is the parameters are identifiable or not, you can use theoretically the phylogenetic invariants or the topology invariants also to study this. This is work of Allman and Rhodes in many different papers. Inequalities, I've been talking only about polynomials, but probabilities are positive, and we have not been using this. They can be incorporated, like Eric Madsen, you did something like that in a paper, and also most recently Allman and Rhodes and Taylor have also some results that involve inequalities also, and also some new paper by Kayakubias. It's not published yet. And the linear invariants, as I said before, they are not very successful for just considering the topology reconstruction, because that was like using a box to estimate a surface, but they are very important in order to detect the model that best fits the data. And we have some results on that direction, but certainly could be improved, and many more work has to be done in these different areas. And there is a nice area. This is a nice area of research and very active now. So I just put here some references that I would like, if you want to have a look at. And I think that's all. So thank you very much for listening to me.
Thank you very much, Marta, for a very clear talk. It's very interesting. So I'll start out with a question from Joe Felsenstein, who I think he's just pointing out that regarding the topological invariants, well, I guess the edge invariance statement about the edge invariants are sufficient.
Yeah.
But he was just pointing out that the other phylogenetic invariant power, if if you're using all the invariants, it should be as powerful as maximum likelihood under the correct model.
Okay, I didn't hear the whole question, but I think that concerning that.
Maybe I'll just summarizing. So he says using only the edge invariants is not guaranteed to give you high power. In particular, it's not high enough to be almost as powerful as the full set of invariants, which would be equivalent to maximum likelihood.
Okay, I disagree. I totally disagree. We did simulation with the full set of invariants. Actually, the full set of invariants is an infinite set, so you have to choose some of them. So for example, for the cumulative parameter model, where I presented that ugly polynomial, there are 8,002 of such polynomials that generate all of them. We used either that set or only the edge invariants. And you get much more successful result with only the edge invariants, because these are those that tell you something about the topology. The others only add noise to your data. So you just need the edge invariants. Instead of edge invariants, you can use some other set, but don't add noise considering all of the invariants. Okay.
Interesting. I guess while we're just chatting, you might as well unshare your screen, because I don't see any questions that are people are in need to refer to your talk. So you said that it's work in progress to use like these larger sets of invariants.
Yeah.
So is that like, can you tell me about that? Although it would be wonderful if we could use more than the quartet methods, right?
Exactly, it would be great, but at this point we don't know how to compare splits with different sizes. And for that we need to have a distribution of the score. And that's what we don't have, because it's quite difficult to get, because it's the last singular values of a matrix, and well, the distribution is not so well known. But I think that people is working in this direction, and we may have results soon on this. Although, as I said, as I presented, the results on quartet-based methods are really good in this case. So I don't know if using the splits, larger splits, would give us better results. What is interesting is that using larger splits, we could evaluate maybe not reconstructing the whole tree topology for n leaves, but evaluating certain splits could be certainly be done with this method.
I guess before I've got more questions, but before I just prattle on, I should remind people to ask questions by tweeting to Philobabble or by joining IRC as described on the website. I guess the one bummer about just using quartets is if I understand you had this 4n+1 thing. I mean, you can that limits you to 3 components of your mixture, right?
Exactly. For quartets, yeah, that's true. If we could use larger splits, we could increase the number of mixtures. The good thing, though, is that instead of nucleotides, we use amino acids. Then instead of 4 times m, would be 20 times m. So there is much more room for mixtures. I haven't tried using amino acids yet, although I have all machinery ready. That would be one of my next goals. And I hope that we can use a larger number of mixtures, and that gives some more power to the invariants.
Yeah, that was another thing I was going to ask about. I mean, I would say that like the real issues with long branch attraction, when people are actually trying to figure out what these deep branches in the tree are, have been really nicely outlined by people like Nicolas Lartillot, and we had him a little bit earlier in the phyloseminar. And the real problems happen when you have sort of a limited set of amino acids that you can have at each site. And so then you truly do have sort of conversion evolution. And I do wonder, like, will the invariants work sort of as well as his highly parameterized models that sort of model this type of process? So.
Yeah, I have no idea. I think that we should adapt them maybe to deal with this type of data, probably. Yeah, not observing all amino acids in all sequences. Yeah. Probably they could be adapted somehow, but at this moment it's not done yet.
Cool. So is there, I mean, I feel like you gave us sort of an intuitive reason why you need to make this sort of normalization for Eric +2. But is there like an underlying mathematical reason why this would be a reasonable? And
Yeah.
if so, would it like lead to other sort of generalizations of that?
Yeah, if you have a perturbation of a rank 4 matrix, and you want to evaluate how far, and you want to use this perturbated matrix to evaluate the rank of the original matrix, then it's important to rescale all the columns and rows in order so that your method, at least the SVD method, works well.
Okay. Let's see. Yeah, any other words about future directions that you see this area going?
Well, I think that not much work has been done on real data, and I hope to work on this amino acid data soon, and to try to recover very ancient phylogenies, but I'm not sure whether we will succeed or not. There is new work by Allman and Rhodes on the coalescent model, proving the identifiability, and this is very, very powerful because they give their scores are the certain probabilities of splits under the coalescent model, and leads to new methods to deal with the coalescent on the incomplete linear sorting problem. And I hope that in that direction there is also much thing to be done.
Yeah, I guess next time Laura Kabatka is going to be talking about the coalescent.
Yeah.
So just so we know, like if we wanted to like rock up and use Popstar's implementation of Eric SVD, I mean, what is the order of magnitude we should be able to run? Like how many taxa? And how? I mean, I guess the sites are really not a problem, right? I mean, sites you could have.
Sites no, the sites are not a problem, but I think that the implementation in PUP is for quartets. So you need to use quartets always. We don't have an implementation that deals with any type of partitions. Okay.
I'm sorry, but how many taxa? Maybe I just didn't hear.
No, you just have to deal with quartets, 4 taxa.
Right, but whatever your quartet combination method is going to have to combine all the different quartets. So that's
okay. But the implementation in PUP only uses the direct implementation of Eric +2 is just for quartets. Then we have used this with an implementation of quartet puzzling or white optimization, and then you can use this depends on the quartet-based method you're using, probably the number of taxa. Yeah, and this work on quartet-based methods is not published yet, so it is preliminary results.
Yeah, I mean, I guess that plot that you showed about like moving along, like the different processes happening at different parts of the alignment does make me think like, yeah, recombination detection and things like that. I mean, it seems like this could be a potentially useful method.
Yeah, this is what work of Allman, Rhodes, and Kubatko, and I think it's very powerful also in this. And also, if we had what I mentioned, we had a way to evaluate how big or how small the scores are for larger splits. So if we had a distribution for the score, then this would be even more powerful.
Cool. Well, I think that is all the questions. Thank you again for an awesome talk. And I guess the next one will be Laura Kubatko speaking on May 31st. So looking forward to that. Thank you very much.
Thank you.